Good afternoon, and welcome to this third session of the webinars organized by FFplus team. So we host on behalf of the FFplus project these sessions dedicated to measurable impact, spotlighting the real-world results delivered by the FFplus Business Experiments and success stories. So FFplus is the successor of the Fortissimo program series. It's a European initiative helping SME and startups to sharpen their competitiveness by accelerating the adoption of high-performance computing and artificial intelligence. So this opens the door to supercomputing resources, and FFplus by this enables companies to tackle complex challenges through advanced modeling, data analytics, and generative AI. So over the next 2 hours, you will see how HPC translates into concrete competitiveness advantage for SMEs. So our speakers will share how they applied this technology to solve business critical problems and unlock growth. So let's start with the first presentation, dealing with high throughput numerical simulations with HPC and AI for precision engineering in welding and additive manufacturing. So this precision will be made by Amin Azhar. Amin is a material scientist and mechanical engineer with nearly 20 years of experience advancing welding and additive manufacturing across research, automotive, and energy sectors. As founder and COE of 3D Components AS, Amin focuses on translating deep tech innovation into scalable industrial impact. He is the inventor of the RobTrack system, which is a robotic welding and additive manufacturing platform that combines physics-guided AI with high-performance computing to rapidly screen and qualify process parameters in minutes. So, Amin, please, the floor is yours. I will stop sharing. You can share your slides.
Thank you, Samir, for the introduction. Good day, ladies and gentlemen. My name is Amin Azhar, as Samir mentioned. I'm the founder and the CEO of 3D Components, and we are located in Oslo, Norway. And today I will be presenting the achievements in our KPM project. So our project, which is called ShapeAM, is a successively delivered project. It was a tri-party consortium to address the challenges and implement a novel approach. So 3D Components is a Norwegian SME, which is specialized in welding and additive manufacturing processes. And we are the inventor of the RobTrack system. SimEvolution is a Danish engineering company specialized in advanced finite element simulations, and Sigma 2 is a Norwegian HPC provider, which is helping us to port our batch and multi-core simulations on their facilities. So selecting the correct process parameters in welding and metal additive manufacturing is crucial because improper cooling rates can alter the material's microstructure and compromise its performance. So currently, these parameters are determined through costly trial and error approaches, and it generates waste and raises environmental concerns. Additionally, process parameters are toolpath dependent, meaning that changes in the position path can lead to uneven cooling and material inhomogeneity. The figure of an aerospace nozzle that I'm showing here demonstrates how reducing the diameter while maintaining the same parameters can significantly affect the cooling rates. So let's assume that we want to perform additive manufacturing of a component that is shown here. The task starts by slicing the geometry. So there are different slicing parameters governing the toolpath planning, among which the layer thickness or the height of the deposition. We can choose a layer thickness of 3 millimeters, which results in this toolpath, or we can choose 5 millimeters, which will look like this. However, a key challenge remains unresolved. The engineers are struggling to determine which of these parameters will be viable in real-world operation and which specific process settings should be selected for each of these cases. The current practice is to find out the answer to this question by running trial and error campaigns, which is costly and it's not environmentally friendly, as it produces waste and it proportionally increases the time needed to manufacture a component. Therefore, the entire process is inefficient and requires the technologies to tackle the challenges. Yeah, to define an accurate toolpath, we must understand single bead morphology, which is strongly driven by process parameters. We therefore need a system that maps parameters to bead geometries. That is the purpose of our proprietary system called RobTrack. So we deposit bead series while systematically sweeping the parameters, scan the bead with the linear laser profilometer, and use the dataset to train an AI model for morphology inferences. However, users also want physics-based guidance on these parameter choices and how they impact the toolpath design. Today, this is typically requires kind of expensive in-process sensing or time-consuming post-mortem laboratory analysis. In ShapeAM, our approach is to run DOE studies and automatically generate one-to-one multiphysics finite element models. Because these simulations are computationally expensive, we run them in parallel on HPC to reduce the time to solution. Then use the results of the simulation, the physical outputs, to further train our AI algorithms. This workflow was enabled through close collaboration across solution providers, HPC partners, and the software vendors. As the most prominent achievement in our project, we can mention the development of the end-to-end software solution that ShapeAM project helped us to develop and deploy. This new functionality in our RobTrack software allows our customers to prepare, submit, and post-process the finite element simulations directly on HPC, all automatically. Once the cases are solved, we can then automatically collect the results and post-process and analyze them. This is, in fact, our original design of the software that we developed during the project. And in a few minutes, I'll be showing the latest version, which is a step up to what you see here. So here is a simple example of how our system can be used. In a complex shape where geometrical features are changing, we may need to decompose the domain and design different toolpaths. Changes in the toolpath require changes in the process parameters accordingly, and the current challenge is how to define and fine-tune them in a quick and reliable manner. The trained AI model in our RobTrack system contains the information that's needed. We just select the right range for the processing parameters, and the AI model will recommend the possible morphology. We then use these values to slice different regions of the geometry and create the toolpath. So the impact of our solution would be to reduce the pre-processing time by more than 50%, reduce manufacturing time by more than 30%, and reduce the qualification costs by more than 40%. RobTrack is built for 5 distinct market verticals, all served by one core engine that turns process physics into qualified welding and additive manufacturing parameters. This engine builds on what ShapeAM has delivered, an HPC and AI simulation pipeline that generates parameters in minutes rather than weeks, and enables digital certification of the entire process. The 5 target audience reflect the full value chain. So component producers and repair teams use RobTrack to dial in the process parameters fast. and build towards digital certification. Consumables and metals developers use it to replace slow and costly physical trial campaigns, and R&D institutes and universities run systematic studies linking process parameters directly to the quality of the material, and the CAD/CAM software providers can plan a robot toolpath from real process physics and removing the guesswork for their users. Last but not least, machine builders embed RobTrack as a built-in intelligence layer inside commercial wire arc additive manufacturing and robotic welding systems. So, how much computing power did this actually take? We ran on Sigma 2's Saga system, part of the Euro HPC network, and we were using up to 600 parallel CPU cores and about 30,000 core hours of compute time. And the reason we needed this scale is basically the physics. We ran thermomechanical simulations on a dense mesh, and we are not running only one, we are running a whole design of experiment campaign, dozens of cases at once, which fills up the 600 cores. So what did HPC buy us? It ended up with roughly a 200-time speed up in process development. Things that used to take months now takes hours, and certification drops from about 6 months to under 3 days. That is the difference between the laboratory demo and something that you can actually deploy commercially. You may even ask if we could do it without HPC. The answer is straight no. 30,000 cores, 4 hours, is about 3.5 years of computing time on a single machine, on a desktop machine. Running these campaigns one after another on a workstation just isn't really realistic. HPC is what makes the dataset and the AI models built on it possible at the first place. Because of the developments in this project and the clear technological advantages, we have successfully signed a deal with Siemens to become their official technology partner. We are going to implement our solution in the Siemens NX, one of the major CAD/CAM softwares in the field. So Siemens NX is among the market leaders in the field, and we will have access to their pool of customers to accelerate our sales and services, and our developed solution will reach to about 2,000 active users that can potentially generate a revenue of 2 million euros for 3D components. Also, we are currently communicating with the other CAD/CAM software vendors to implement our solution there as well. And it's expected that we close a partnership deal with 2 new manufacturing institutes by the end of 2026. This slide looks at what ShapeAM means for Europe as a whole, across 3 main dimensions. First, added value is competitiveness. The robotized welding and additive manufacturing market is heading towards 83 billion market by 2030. ShapeAM gives Europe a sovereign computer-aided engineering and AI stack for the market towards reducing the reliance on non-EU systems. Second added value is about citizens and environment. By cutting alloy waste and CO2 emissions by up to 90%, the workflow directly supports the EU Green Deal goals, while also creating high-skill manufacturing jobs. Third added value is scalability. The workflow runs on any Euro HPC and any national system in any member state of Europe, across any sector such as automotive, aerospace, energy, shipbuilding, and you name it. We also implemented a low-cost software as a service model that we call it welding as a service to make it more accessible for the SMEs. The bottom line is that we developed a system that offers one workflow on any Euro HPC site and in any region that directly translates into a sovereign, green, and ready-to-scale system. So even though our solution can recommend process parameter, one critical question remains unanswered. The question is whether the selected and validated parameters are truly suitable for a specific part geometry. To answer that, we are currently exploring the physics-enabled generative models, which the goal is to leverage the HPC computing to evaluate geometry-specific feasibility more rigorously. In parallel, we are also investing in a potential to position our solution as an add-on to established engineering software such as Siemens NX, as I mentioned, and Simofact, the finite element software. And we are developing go-to-market strategies together with our partners. So finally, we plan to publish scientific articles summarizing the key developments and the outcomes of this project. On this slide, I would like to show the latest version of our software that was developed after the ShapeAM project. By showing this, I'm trying to put this as an evidence that the achievement in the project was not just a one-time development, and it is such an integral part of our solution that we developed it further after the project ended. So I will walk you through the short video here and demonstrate the example. So here, after we have run the design of the experiment and collected the data, all the data is loaded here, and we can just basically view them in a tabulated way, and we can sweep among all the cases that we have been depositing. And it shows that the morphology of the beads are also changing, but we don't really know about the physics as we speak. So we select the thermomechanical analysis here and then generate the batch files. So here the user doesn't interact with the conventional features of the finite element simulation, such as meshing, because that has already been taken care of, and that's scaling on the back end, completely automatic. Then we want to execute this, and the software shows that it's not connected to the Saga system, the Saga server. Now the connection is established, and then we go to the sim intent page, and then we basically start to execute these batch simulations in parallel. As you can see, they're running all in parallel in a much faster way than it could possibly be achieved in a desktop system. And then we generate the cooling rates, like as you see here, for different cases, and even residual stresses as a result of this, because residual stresses are very much dependent on the process parameters and the shape of the bead that is deposited. And then after we are collecting all these data, the physics data, then we add this to our AI model that contained the geometry from before, and then we make a kind of physics-informed AI model to be used further for the development of the process parameters. So during and after the ShapeAM project, we participated in a few events and conferences and even published popular magazine articles about our developments. Our objective was not just lifting our product and the brand name, but also demonstrate how FFplus and EU investments support our progress along the way. I'm also pleased to inform you that we have just been accepted in the Google DeepMind Accelerator program due to the fit of our product to the Physical AI initiative of Google. We are hoping that throughout this program, we'll be able to be more visible and learn more about the most advanced technologies and implement them firsthand in our products. We are also actively looking for investors to scale our company and team and fuel our future activities beyond our current achievements. That was my last slide. Thanks for your attention. I'll be happy to answer any questions if you have.
Thank you, Amin. This is all this interesting presentation and these interesting developments with a huge impact for your company and for the ecosystem, European ecosystem of additive manufacturing and welding. So I think that the additive manufacturing is one of the technologies which is developing during the last decade, very used in automotive and perhaps now in aeronautics. Are there any questions from the attendants? Yes, Marco, please.
Yes, thank you. Very interesting study. Congratulations, and hope the best for the success of the business, really. I have a curiosity because there are similar things, even if the application is totally different. And it's about the FEA software that you are using to create the data, about the licensing model and the licensing costs that are related to this, because it's a matter of fact that we are now using high fidelity simulation as FEA and CFD to create so-called foundational models, for AI. It's maybe too much say foundational models, but let's say we can create for specific application surrogate intelligence that can work. So for sure at deploy, no, we haven't, the business is in our hands. But when we create the data, it's really important when you crunch the data about the licensing model and the licensing cost, especially for the efficiency. So your take on this will be good.
I must say that, I mean, in our previous sessions that we presented this, we have underlined this as our biggest challenge, to be honest. The software license for 600 cores, it literally costs €1,000,000. I mean, that's the price tag that they are selling it. And we got this software with 99% discount to be able to basically basically use it in our system. But there is a strategic reason for that. This Simofact people who are the owner of the software, they were really interested to see such applications as like an add-on to their system. And we have a strategy to how to deploy this. Simofact, they have Nexus cloud computing platform, which they are not charging for the software license. It is per computational core that is solving on their system that the user pays for that. It makes our life a lot easier if you embark ourselves on that Nexus system, but it is still HPC.
Thank you for this clarification. I'm also happy to see that the collaboration with Siemens is it's a European collaboration, and this will reinforce the sovereignty of Europe in this field. Thank you very much.
Thanks. Thanks.
Okay, thank you. Let's move now to the second presentation, which is about HPC for RF subsystems made by Erika Meniconi from RF Microtech. Erika earned her Bachelor of Master's and Master Science and PhD degrees in Electronic and Information Engineering from the University of Perugia between 2007 and 2015. Her early career focused on RF MEMS and satellite communications, featuring a long-term collaboration with Airbus, Defense and Space. Spanning her master's and PhD research during this collaboration. So in 2014, she joined Corvu Munich as a senior design engineer specializing in BAW filters for mobile communications, and later advancing to design engineering manager. Since 2025, she has served as a senior project manager at RF Microtech in Perugia, where she leads product development for space applications. Please, Erika, it's up to you.
Thank you. And so my talk is about HPC for RF subsystems, and I am from the RF Microtech company. And in this few times, we'll talk about how we implemented APC in the RF subsystem design. Which for our case, specifically for space application, designing this RF hardware is slow, expensive, and it has constraints by physics. And as was mentioned by the previous presenter, even in our case, without HPC, is often based on some level of try and error, which is costly and also not environmental friendly. So RF components are essential building blocks of the modern space systems. And the requirements are becoming more demanding, higher performance, compactness, and also shorter development time. So for this combination of challenges, it creates really a challenge on the engineering team to respond in a very short time and with high performing products. RF Microtech has more than 18 years of experience in developing customized RF solutions, and we operate mainly in the satellite communication space system and also aeronautical applications. In particular, I'm on the space systems area. And of course, we focus in delivering high-performing RF hardware, and our main customers are across Europe. So the main difficulty for the RF design in the space environment is that it's a multi-physics problem that we need to solve. It's not only about electromagnetic, but we need to take care of thermal behavior and also mechanical constraints. And we cannot treat each aspect independently. The problem is that in our design at the moment, they are not fully integrated, these three domains. And if we look at the today workflow, what we have generally is that we start with the RF optimization, then moving to the mechanical design, validate at the simulation level the mechanical design, fabricate, test, and then fix whatever is not working. And if there is a problem, we will find at the end of the workflow, and we will need to restart from the beginning. So this is inefficient, generate waste, and often the optimization starts at least from the second run. So it starts late in the process. So the main limitations are three, and the computational power, a limited computational power is a heavy limitation because it prevents us to have a high, to have model with high accuracy, and sometimes prevents also to simulate models if they are very complex. And the second limitation is that many decisions are based on experience and on best practice, so are not outcome of an optimization, and there are always trade-off between time, cost, and performance. So the final solution is generally not the fully optimized solution, but is an acceptable solution within the constraints that we have in the projects. And thanks to HPC, we can bring this high-performance computing in the design loop and have a strong interaction between RF optimization and mechanical design. This was possible thanks to our partner in this project with Open Engineering, and was providing the software for that. and parallelizing or having a strong interaction between these two phases, and also increasing the model accuracy thanks to HPC, enable us to achieve a full multi-physics integration development and to have a real co-optimization and reduce the development cycles. So how HPC changes things? Basically, there are three things that are fundamental and that were enabled by HPC. First of all, the speed. So simulation are much faster. And then the accuracy, because we can run models with much more details. And the iteration, so we can run, we can explore many multiple designs in parallel instead of waiting for the fabricated model, and reduce in this way the manufacturing cycles. And as I mentioned before, high complexity model can be optimized thanks to the potential of HPC. So with this project, we achieved technically up to 60% speed up and even more. So it was tested multi-GPU from 1 to 4 GPUs. And also we had simulation with more than 17 million degree of freedoms running in less than 2 hours with 8 computed nodes. So generally we have those simulations running over a weekend, and we achieve also a high scalability of the MPI version of the FEM. And this translates in practice to a reduction of design time of about 50%, and also reduction of the weight of the product, of the solution, of about 40%. For a satellite, it matters. And reducing design time has a direct impact on business, and is a measurable impact on economic and social aspects. So surely there is a reduction of the cost and also a market speed up. And for the particular products that we have used as a vehicle of experiment, which are characterized by a low production volume, and therefore the design is having a major weight on the total cost. We have a 25% of total cost reduction, and also a faster development allow us to be faster, to have a faster time to market. Which is important because sometimes we cannot satisfy customers, and we cannot take product development because of the time constraints. And this translates for sure in a higher customer capacity. And beyond this individual project, there is also strategic impact for Europe. The collaboration, the partnership was with another European company. And this can strengthen the EU competitiveness. In particular, we support key space initiatives in low Earth orbit missions and also lunar missions, and which are typically we are in a field that traditionally was dominated by non-European players. And as I mentioned before, our main customers are European customers, and are all involved in European space missions. Looking ahead, this can be considered as a starting point, I would say, and we are continuing to develop this approach. We could verify the capabilities, but for sure there is the need of further development on the software side to achieve an hybrid MPI and GPU solver, but also on our side to expand prototyping capabilities and also to scale the adoption to other industrial applications. The method is scalable, and it's a matter of refining the workflow. Thank you very much for your attention. If you are curious to learn more about our products, or if you have further questions that we don't have time to address now, you can reach us.
Thank you, Erika, for this interesting presentation and the success story. Any question?
Yeah, I have one, if possible.
Yes, please.
Yes. So very interesting, and I have a curiosity, especially about the CAE technology you're adopting, and the questions indeed are two. One is overall about this technology and what is the model for use this CAE approach, and the second one is very specific and technical. So it's about the coupling of mechanical and RF analysis, especially to understand whether for the specific case you're studying, the mechanical analysis is just not an assessment, not that everything is fine on a mechanical point of view, but if this mechanical analysis is a clue to understand the format, the working shape of the component can affect the RF performance. So very technical. Thank you.
Yes, so for sure, I start from the technical, and then maybe you can repeat the first question. My memory is not so long. So the model considered many of our products are based on cavities and waveguide technology. So we do cavity filters, and so the mechanical structure is also the one that is creating the RF performance. And if the mechanical structure need to change because does not satisfy the mechanical requirements, then we need to go back in optimizing again the RF performance. And at the moment, this link is missing. So having everything at once that take all the requirements as an input would enable to have one optimization flow instead of having iterative and sequential flows.
Yeah, many thanks. And the CAE solution you're adopting so is today streamlined so that both the analysis can work together. So you get KPI at the same time on the HPC, I understand.
Yes. So you can yes, with the potential of the HPC and also for sure HPC helps to reduce time. So if you have as I mentioned before, if you have a 3 days simulation that you can run in 2 hours, it's a big step further.
Very good. Thank you.
Thank you.
Thank you.
Any other question? No. So let's move now to the third presentation, which will be made by Jelena Joksimovic from Rudolfovo. and which is dealing with HPC-enabled deep learning for real-time energy forecasting in buildings. Yelena Yerkimovich is a researcher specializing in industrial artificial intelligence at Rudolfovo, the Science and Technology Center, Mesto in Slovenia. She holds a bachelor's and master's degree in mathematics and a PhD in computer science. With expertise in time series analysis, she develops advanced forecasting models and optimization solutions for energy management systems, contributing to more sustainable and efficient energy use. Her work combines state-of-the-art artificial intelligence methods with practical industrial applications, fostering innovation in energy optimization and decision support systems. Please, Yelena, it's up to you.
Thank you, Samir. Hello, everyone. My name is Jelena Joksimovic from Rudolfovo Science and Technology Center in Slovenia. And today I'm going to present a project named aimed HPC, which is HPC-enabled deep learning for real-time energy forecasting in buildings. So Robotina, our lead partner, is Slovenian SME, and they are developing already for 2 decades IoT-enabled hardware and cloud software solutions, primarily for smart buildings, industrial automation, and they are focusing lately on energy management systems. So prior to this Fortissimo project, they already collaborated with us on the same problem. So they needed accurate energy consumption forecasts at 50-minute resolution for buildings they are already operating with. So based on smart meter data, we already performed analysis, and we discovered that deep learning models such as BLSTM recurrent neural networks were the best candidate for accurate predictions. However, these models were too computationally demanding for Robotina's current infrastructure. So during the project, we developed HPC-enabled forecasting workflow that connects Robotina's energy management system platform with resources from a supercomputer. So we combined real data, historical data with market, tariffs, weather data, and we used all this to find the best architecture and to train our models. Specifically, we used Vega HPC in Maribor in Slovenia. So what we did is we primarily did neural architecture search, so we know which parameters are best for a particular user, and hyperparameter tuning. And our final output is not only validated forecasting pipeline, but also lightweight version of the model that can be really deployed on edge devices. So the main parties that benefit from the results of these projects are facilities managers in buildings, building owners, energy service providers, so anyone who operates the building, actually. And so our target group are offices, hotels, big buildings, public buildings as schools, medical centers, shopping centers, etc. So significant energy users. So they really need better planning and optimization, so they really benefit the most from the product. Also, who can benefit are other SMEs that already, like offer renewable energy services and hardware. So this can come as added value for their customers. So what happened during the project? The tasks that were almost infeasible for us. I mean, we could have trained the model without HPC. However, we couldn't do a broad architecture search for the model, so we could just guess parameters and then train, and it was like try and fail, while with HPC we could just do a broad search of all parameters. I mean, not all, but a wide network of parameters, and find out which are the best, give best results. We used 4 GPU nodes in parallel, and 50 node hours per one build. So HPC was practically enabling the solution. So for Robotina, the value of this product, of this solution, is potential annual revenue of 80,000 euros based on a subscription model. And for end users, as buildings, we can say that biggest impact is that they can be more sustainable in their operations. They can spend less, save up to 10% on costs. And having this HPC edge workflow is really helpful because it can, something that is complex, some complex solution is available for end users to be deployed on their own, at their own place, let's say. So for Europe, finally, biggest impact is reducing strategic dependence on energy import. So as the conclusion, we invite all building operators, energy service providers to be a pilot users of this solution, to collaborate with us on the deployment, next phase deployment. The solution is ready to support operation of smart buildings, lower their costs, so everyone is welcome to contact us. And that's pretty much it from me. So if you have any questions, I'm here to answer. And David, who is CEO of Robotina, should have been here, but we were supposed to be at 3 p.m. So he's not here. Yeah.
Okay.
So I will give my best to answer everything.
Thank you, Elena, for your presentation and for this work made by your consortium. Any question? Do you have any quantitative evaluation of the savings of energy or costs when applying the solution you developed?
Well, we did some tests internally, and it's 10% currently what we had on our test users. From 8% to 12-15% is, yeah.
Okay. Any other question? You will continue the developments, I suppose, of your product.
Yes, we are continuing the development and installations in
Okay.
Robotina's customers who already use some other solutions.
Okay, good.
Thank you.
Thank you very much. Okay, now it's Marco's turn to present the success story dealing with from HPC to clinical practice, defining pre-operative planning for vascular graft surgery. So Marco Evangelos Biancolini is an associate professor of machine design at the University of Rome. He is the creator and developer of the industrial software ABF Morph and served as the principal investigator for the H2020 Meditate project on medical digital twins. His research focuses on engineering applications of fast radial basis functions, mesh morphing, shape optimization, and reduced order model for digital twins. Marco, please, it's up to you.
Can you see my screen?
Yes.
Okay. Thank you very much for the introduction. And I want to complete my introduction. You can notice my affiliation is Live-Gemini. I am a co-founder of this startup, MedTech, that originated from a Marie Curie project that was concluded last year, just to complete. And you see here, Live-Gemini, no, under my affiliation. So the title of my talk is From HPC to Clinical Practice, Redefining Preoperative Planning for Vascular Graft Surgery. So I start with a brief introduction about Live-Gemini. Live-Gemini, as I have mentioned, is a medtech startup that originated from a large European project, Meditate. Meditate stays for Medical Digital Twin for Aneurysm Prevention and Treatment. So we are applying medical digital twins with a specific focus on the cardiovascular sector. And Live-Gemini is attempting to bring what built during this very long research to products for supporting the clinical decision, especially with the focus for the aneurysm. And in doing this, Live-Gemini is currently active in R&D activities that are R&D for developing our technologies, but also to support our new customers, and in developing software products that are intended to deploy medical digital twins in clinical practice. And we are a small but committed team. You can see our pictures here. And we have some key point of offering our services. So for supporting clinical decision, we want to use best-in-class in silico approaches that have to be easy to be used, quick, but accurate, of course, because we are helping healthcare treatment. We work in a multi-platform to simplify the deployment. We consider that in typical medical structure, there are many options, so we are supporting but the Mac Windows. And last but not least, we have a very strong focus about data control and security, and all of this to get to this market who is involved knows this very well. It's a very difficult market because even if you are not working at a new drug, you have that the certification process you have to go in this kind of market is very long and complex. And we are active in a different research project. This slide is from our standard introduction deck. And in our introduction deck, you can see that FFplus is in this slide about our European project. And so today I will tell you a little bit more about Pandora, that stands for preoperative assistant based on data-driven approaches for vascular graft surgery. And in this business experiment, four of us, the company that is delivering the new product is Gemini, that work assisted by the software CA company RBF Morph, and to university Lyon and Rennes in France, University de Rennes and INSA. And all of these and all these tasks, so from the hospital, from the material characterization for INSA, advanced methodologies, was used to put together this new product to face the challenge of supporting aortic graft surgery. Because in this kind of treatment, the percentage of secondary intervention is very high. And so a better matching of the prosthetic part with the patient anatomy, it's really a paramount, and this is where we are working on. So with Pandora, we want to deploy the best-in-class high-fidelity simulation in a real-time application, easy to be used. And to use this and to put this at work, we are doing something that today is becoming quite a standard, no? We call them foundation models. So we can say that with Pandora, we are creating a foundation model for the treatment of this particular surgery. So this foundation model can be adapted whatever is the anatomy of the patient, and looks for the perfect match for the prosthetic part size and prosthetic implantation. So we are speaking for sure we are now interacting with cardiovascular surgeons, with healthcare staff that is active in advanced research. We are, on the top of the technology, something that is new for this specific field. We are also speaking with the medical device manufacturers that are highly interested about a better adoption of their solution. But all in all, what we want to do is to provide something that helps the patients. So the final goal, of course, is to reduce the risk and to have a better outcome of the treatment that is deployed with this approach. I have a couple of minutes of video about what the software is today. So I will run and commenting what's going on. So you see we have this UI. We can read in a DICOM file, that is the standard way of representing the anatomy. And you have in the view the patient ready to be treated. And in the area that you can see, you have this replacement. And the study of this replacement is very difficult because it requires a very complex nonlinear analysis. And this nonlinear analysis allows you to do what you can see in this kind of animation. So it's the process of putting together the prosthetic replacement. A patent is pending about the approach we are using for the advanced simulation. And as you can imagine, what you see here going in real time, so you see the software that allow you to go from patient to patient, push one button, run suture simulation, and see is in less than a second the results there, is because behind this software there is this foundation model properly trained to be fast but accurate for the prediction with specific patient. In the demo that is rolling, you see 3 different solutions for the prosthetic part and how the match is changing for the patient number 1 and patient number 2 and number 3, sorry, of course, are anonymized. And this gives you an idea of what the surgeons are today testing to use this technology. So what is under the hood? I will not go technical today, but just to give you an overview, also to understand why we have this HPC need. So we have to create a solution that is suitable for whatever patient is arriving. So to use this, we use a method that is called statistical shape modeling. So we use a cohort of actual patient. We expand this cohort, but we use synthetic. Overall, we are using 256 possible patients. Okay, so the cohort is quite large, and this cohort is used to train the approach and to create the foundational model. For each prosthetic solution, we test this on all the individual of this cohort. We run for each, it's an implicit FEM, sorry, it's an FEA analysis, highly nonlinear. We use LS-DYNA to do this. And we create from this simulation data snapshot. So we are creating a synthetic data set. With this data set, as the shape are isotopological, because we are using mesh morphing to map all the model, we can use principal orthogonal decomposition to create a reducer order model. We pack this reducer order model into a component called the functional mockup unit, and the functional mockup unit is ready to go into our software. So all the preparation of this intelligence happens in the HPC, but once the intelligence is there, everything it's easy as using this software. And the data set you create, it's good for a variety of anatomy, will be enriched, adding many other options instead of just 3 for the correction to be tested and matched with the patient. So some figures about the HPC and this project. Here you see out of the 256 shapes and anatomy, we have collected 4 of them, just to give you an idea of the variability that you have in shape. This set indeed originated from actual patient. We haven't so much patient, so we used an original database of 73 patients, and using statistical shape modeling, we expanded this data set, creating 2,000 synthetic anatomies. Out of the 2,000, we selected a subset, so the 256 that are good and were all of them inspected to be to sound as credible anatomy. So we will not just trusting the AI process for this synthetic population. The synthetic population is important because we need to create the simulation data. 73 are not enough. So we run with this LS-DYNA analysis, and we sum it up to close to be 1 million to CPU core hours. Here, I did the homework about the question that we have about the project, computation scale. So how many nodes GPU were used? This is an important question, especially it's strictly dependent on the software you are using, because here we are using LS-DYNA, but for the specific simulation flow, we need to use the implicit version. And we noticed that this implicit version saturated at 8 cores. So we try to go higher with the number of cores. It was just hosting resources, licenses, but not improving the runtime. So the optimal adoption of our license pools was to use the license we have for 6 runs in parallel. With 6 runs, each one 8 cores, we saturated our licenses. Why I'm stressing this? Because as mentioned in other presentation today, of course, if you have more licenses, instead of 6, you can do 60 or 600 run, of course. And the technology allows you to do this because taking 8 cores 60 times or 600 times is not that difficult. Okay, so it's important to know. And also, the license that you have are related to cost. And you need to pay this cost, yes, because in this sector, for best-in-class and validated process, the LS-DYNA software is recognized to be the standard. So for each variation, we need 256 runs. So we explored just 3, but we should explore at least 30. So the budget we had was not enough, but it was enough to explore at least the feasibility of this project. Each run individually take about 3-4 wall clock times hour, of course, so it's not written. And without HPC, you can clearly understand that it's really hard to figure out how a synthetic data set could be created. Even with the budget of HPC we had in this business experiment, we just created a demonstrator, not the full technology that we need. Here I have another snapshot. Sorry if this is in Italian, but this is something captured in the script we have. We worked with Cineca and with the remote server. And this is about how the analysis were going. You see, completati means successful, failed, or timeout because too long. So it's interesting that here, we didn't manage to complete about half of the run. It's weird, but it's not that strange, because when you are exploring such complex geometry, crunching a lot of data means that you have also a way to create enough data to train your model. About the impacts and the European added value. Okay, so it's quite clear that the in silico and the medical digital twin that is gaining more and more adoption and interest can have really an important impact. We can improve the treatment, and so all in all, we could save lives. So it's really important, the impact we can have. So we are targeting at least to improve the planning of the surgical treatment, and there is also an economical benefit because we reduce the healthcare cost, because the interventions are very costly, yes, way costly compared with the adoption of a software, of course. And there is another important thing. We want to strengthen the European leadership in digital health, AI, and digital twins. The scalability, well, at the moment, we are active in Italy and in France, but we can go further, so across other European countries. We, on the technological point of view, we are almost there. You don't need to have a HPC locally. The technology is easy to deploy, easy technically, because the really difficult barrier here is the certification process, that it's long and painful and requires years. Okay, and we are in the middle of this. Before concluding my speech, I want to give you the experience I personally had with the university and with my company, and also the network I'm working with Fortissimo. Because we started with the first call of Fortissimo 2013, so more than 10 years ago. The experiment name was HPC Cloud-Based Additive Manufacturing. And so in 2013, together with HSL, an Italian company that is active on additive manufacturing technology, and with Lamborghini, we managed to improve performances of Lamborghini Aventador engine. Putting together this business case that was benefiting of the cloud technology, was using the same approach we are using today. 13 years ago was not that common to create such a large number of variation. But what is really important here, I think, is not what we did, is what happened, no? Because we are, no, when we put this success story together, we have to envision what will happen in the future, what will be the impacts, what will be the benefit. After 10 years, you can say. So about this project, I can say that Fortissimo help was really very, very important, because it was not limited to provide a good solution for Lamborghini, increase the power of the car about 6% at that time, but also because we managed to replicate this approach, and we used this approach for similar application, so for thermal combustion engine, inlet, exhaust, for HVAC. So the RBF Morph company and the HSL company worked together and have a significant business impact. And second, Fortissimo 2, some years later, in this case, it was an aeronautical project. We worked at the optimization of an aircraft with Piaggio Aerospace. Piaggio Aerospace was recently acquired by Baykar. On the business perspective, this was, of course, not related to this project, but what we did at that time, it's the improvement of the aircraft, the P180 Evo, defined with this automated process winglet. And the winglet is there, the range of the aircraft is extended, better product. This approach on aeronautical application is now more and more replicated. At the moment, we are working on a winglet right now with fully funded project. We are doing business, and well, what was done at that time resulted to be really successful. Last two, in FF for Euro HPC, we worked on a cardiovascular application, medical digital twin. You can see a lot of Pandora in this past project. It was, we moved first steps at that time, and this other project that is tied about drug delivery. But this project tells us an important thing, that moving and innovate in healthcare is a way more difficult than in other industry, and tools as Fortissimo are really helpful to transform ideas, not just in simple research, but in actual demonstrators that are validated in different contexts. So I can move to the conclusion of my speech. We managed with Pandora to put together the HPC generation of data. And data that are about vascular anatomies that can be used and collected to deploy a solution. I have shown the solution in the video. So we can say that times are mature enough to put together HPC, AI, if we want to call AI, it's machine learning, but today we call AI, okay? But surrogate models are really, really important, and allow to have in a click and in less than a second an analysis that is indeed calculated upfront by a lot of HPC resources, but allow to enable a very interesting model to transform our simulation and our CAE into products. What comes next? We have to move forward with LiveGemini. So to validate on a larger patient cohort, we need to extend the number of graft options to be used and go for the long and complex clinical adoption and all the approval that are required to move this from research to medical practice. Last but not least, the value of Pandora. It's the last step of a journey. So with Pandora, my personal experience, we see how many Fortissimo experiment has been conducted so far, but over the last 13 years, I had the privilege to be active in 5 different projects: automotive, aerospace, a lot of healthcare, and I can witness that this is really boosting the development, the research, but not just the research. At the time of the first Fortissimo project, RBF Morph was just incorporated. Now we are 20 people working on this. So I want to say, and I have to say, that in this path that is making our company successful, and I guess the same for the other companies that are part of this, it's really a great help toward the success. Thank you for your attention.
Thank you, Marco. This was very interesting. And thank you for the series of stories that prove the value of the Fortissimo support, program support across this wide-ranging topics. So the topics are very various through the success stories presented today, but also across your experience with the Fortissimo programs. Any question? Yes, I think we have a question. Yeah, no, just a comment. Just a question. So you use HPC to set up the reduced order models or the surrogate models, then you optimize your design using this based on this reduced order model, I suppose. But you need also HPC later to validate the final design, no?
Okay, yes, this is a good question. Indeed, the core of the HPC in this project, the main adoption of HPC was to crunch the full FEA simulation, because all the other action that are, for instance, the virtual cohort of patient creation by PCA, and all the data you have to do to create a reduced order model, so the compression of the FEA result and so on, it's something that is not requiring a huge HPC. You need, of course, a good workstation, but it's something that you can do in your site. The main need in this project for the HPC is for the creation of the synthetic data set, because to have a good simulation of the graft suturing process, you need to run a simulation that takes 2-3 hours. It works, of course, also on a workstation, but on a workstation you can do one simulation at a time. If you need to do thousands and thousands of simulation, you haven't this benefit. And I want to comment on this. Already pointed out this in my slide. When you need to create synthetic data set, that today it's something that is attracting more and more interest. It's like you do all the simulation up front instead that later understanding what's happening. This approach, of course, it's comes with a very high HPC cost at the beginning. But as you know already upfront what you want to do to compute, you can really simplify the scheduling. Because we know that with the scheduling, we are so struggling, for instance, in a CFD solver to scale up with a number of cores, or also with a FEA solver. How many cores, so how large can be my parallel run? I want to say that here it doesn't matter, because if you have to run 1,000 simulation, and 1,000 simulation, each one requires one core, you can do all the simulation at once in 2 hours. So for this kind of simulation, the scheduling strategy, it's really very, very important. And as I have explained in my slide, we discovered that here 8 cores was saturating the scalability of this specific. So, okay, you have 8 cores with the license. We were able to run 6 run parallel, each one with 8 cores. Of course, this was not the limit of Cineca supercomputer. Yes. It was the limit of our licenses. Because if you want to run more, you need more licenses. And the licenses cost goes up. But this license, it's a really important story, because when you have to we are in the healthcare, but figure out, for instance, the aeronautical field. In the aeronautical field, there are applications that are certified with a specific Nastran, no? So using a specific solver that has the cost, because the reputation and also the stability and the reliability of the results you get builds up after many, many years. So this part of the story, so the CAE solvers licensing, it's really an important part.
Thank you. Thank you, Marco.